Oh. Let's talk about density. We use this symbol, it's called rho. It looks like a P, but it's rho. Rho here is density. And rho can be calculated by taking the mass of an object divided by the volume of the object. The mass over the volume. So for example, we can go to the lab and calculate the density of water. If we take a container, we'll say it looks like this, cylinder, and we go maybe 5 centimeter high. First we take the cup before we put any water in it. We take the mass of it. Let's say the mass before you put the water in it, it's 0.5 kilogram. Then we put some water in it, up to 5 centimeters high, and we take the mass of that. And the mass of that, let's say, is 0.7 kilogram. I'm just making numbers up. And this beaker, if you're looking at it, or this container, looks like a cylinder. So if you're looking from the top, it looks like a circle with the radius of, let me say the container is 5 centimeters. Let's not use 5 because it'll be 5, 5, 5. How about 4 centimeters? So what is the volume of the water? The volume of the water, when you have a cylindrical shape, it's area times the height. And the area is pi r squared times the height. So the water was only 5 centimeter high. So the volume of that is going to be pi times r, which is 4 centimeters, that's 0.04 meters squared, times the height, which is 0.05 centimeter, which is pi times 0.04 squared times 0.05 square, not squared. The volume of the water, it's 2.5 times 10 to the negative 4. So what is the density of the water? Well, what is the mass of the water alone? Well, the mass of the water is what? 0.2 kilogram, the difference between them. Divided by 2.5 times 10 to the negative 4. It says 795 kilogram per meter cube. I made up these numbers actually. Water density is roughly 1,000. If you take a fresh water, the density is almost 1,000. Salt water, 1,030. So water is about 1,000. So I'm not really that far, 800 kilogram. What that means, if you have a container that's 1 meter by 1 meter by 1 meter high, if you make a box, 1 meter long, 1 meter high, 1 meter wide, and you fill it with water, the mass of that will be 700, based on my number here, 795 kilogram. And that's how we calculate the density for any liquid. We can do it for solid too. Same thing. Do you wonder why wintertime when there's ice on the water of the lake, the ice on the top, not on the bottom? Or if you're watching Alaska, some of the shows Alaska, you always see that ice floating on the top because the density of ice is less than density of water. When you put ice in your water to drink it, you always put a few ice cubes just to make it cold, you'll see that ice goes to the top. Density of ice roughly 912. So these are some numbers for density. Gold is really, really heavy. 19,300, that's what the density for gold, kilogram per cubic meter. Mercury is high, Then we get to aluminum, iron. Now notice where is water. Let me find water. Water here, fresh water is about 1,000. Olive oil, that's why it floats on the top, 920. Ice is 917. Alcohol, ethyl alcohol is 806, way less. Wood, cherry wood, 800. You see them a lot of times, you throw a log in the water, that log floats. Another wood, look at this, if you make it out of balsa wood, I don't know, I've never seen a balsa wood, but what is it? It's 120. That should float beautifully there. Styrofoam is 100. Air is 1.29. Helium 0.179. So density changes based on the shape that we use. In movies, a lot of times when you're watching old movies, they show you somebody breaking into a bank and stealing some gold. And you see the thief coming out of the bank with colored bags. They look about, I don't know, something like that. It looks like maybe something like this one, a foot long. Well, a foot long is roughly about 30 centimeters long. By, let's say, 6 inches, that's 15 and 15. So a foot long by half a foot wide, half a foot high. If that's filled with gold, they show the thief coming out of the bank, carrying 2 of them in his hand. There's the thief here, walking out with 2 of these gold things. Well, let's see if that's really close to reality. How much weight is he carrying? You will have to be the strongest man in the world to carry that, probably. A foot by half a foot by half a foot. It's not that big. The volume of each one. The volume is length times width times height. The length is what? 30, that's 0.30. Width is 15.15. Height 0.15. It's 0.00675 cubic meters. Rho for gold. I look at the chart, we just looked at it. For gold, rho is 19,300, which equals the mass over the volume. So the mass of each one of these bricks, each, is going to be 19,300 times the volume, which is 0.0076 or 67, I don't know, 2 zeros, 675. This times this. So times 19,300. Each one of them is 130 kilogram. Well, you don't have to be the strongest man, but when you're carrying 2 of them, what are you carrying? 260 kilogram? How many pounds that is?
Over 500.
572.
Approximately 573 pounds. Approximately 570 pounds. So you got to be really strong to carry that weight and come out of it, running out of that bank with it, with the 2 bags in your hand. So that's how density works. So if you know 2, you can find the third one. Rho equals mass over volume. It depends on the shape. For this, the volume is the area times the height. It's always the area times the height, but the area is pi r squared. For this, the volume is the area, which is this one, times the height. Well, the area here is length times width times the height. That's always the case for the volume. So that's density. It is difficult actually to weigh something like, I got a truckload, you want to fill your water with your pool with water. You got a truckload of water. Well, how much does it weigh? Well, you're not going to pick that truck and put it on a scale and say that's that many pounds. So you look at the volume of that tank. You say, well, this pool is 10,000 gallons of water. Well, you take a gallon of water, you can weigh that, or you know the shape of it, the volume of it, you know the mass or density, you can calculate what the weight of the water there, or the mass of it. If you know one, you know the other one. What about pressure now? Pressure, we use the letter P. And pressure is defined as the force divided by area. Force divided by area. If I take a balloon, this is the balloon here, tied with the string, excuse me, and I take a pencil like this, there's a pencil, and I'll try to pop the balloon by pushing with the eraser side of the pencil. Let's say I put a force of 10 Newton. I'm pushing on it. You'll see the balloon is denting, but it's not pop. Probably will not pop. Well, if you look at that pencil here, if you look at the end of it, it has a diameter. Let's see how many millimeter that is. One, two. Oh, I'm sorry, I'm looking at the wrong side here. About 6 millimeters diameter. So this is the pencil. It looks like this, the other end of it, the tip of it like that. Now the same balloon here, now if I flip the pencil, I use the sharp edge now to pop it. I push with the sharp end with the same force. But now the diameter of this sharp edge, if I put it against this, it's probably 0.5 millimeter, probably even less than that. I'm pushing with the same amount of force there. What is the pressure on the balloon in both cases? Well, let's look at this case. This is case 1, this is case 2. Pressure through case 1, it's force 1 over area 1. What was the force? I apply a force of what? 10 Newton on both cases? And what's the area? That's pi r squared. What is r here? 6 millimeter. These 6 millimeter. R is what? 3? 3 millimeter divided by 1,000. Pi r squared. Area of a circle, pi r squared. Ten divided by pi. Oh, turn it on first. 10 divided by pi. Oh, 10 divided by pi. God. Try it one more time. 10 divided by pi. Try to rush through it. Divided by 0.003 squared. So the first pressure is 35367. The unit for that, Newton per meter squared. Again, the area for a circle is pi r squared. That's what I'm using. Let's see pressure 2 now. Force 2 divided by area 2. When you flip that pencil to the sharp edge, wait till you see the pressure on that now. It's 10 divided by pi, and R here is what, 0.25 divided by 1,000 squared. And the answer for that, pressure 2, is 5092952. What is the ratio of pressure 2 to pressure 1? Curious, how many times bigger? Divided by 353677. It is 144 times larger. So when you take a needle and you touch a balloon, there it pops because the pressure now, it is 144 times larger than if you stuck your finger, baby finger. Maybe about 200 times bigger if you stuck your baby finger. That pressure sounds like a large number, right? Do you feel the air pressure on your ears? Anyone feels them? You guys feel anything pushing on you? Well, we have air pushing on us right now. We just like, when you go in the water, do you feel the weight of the water pushing on you? Especially if you're deep enough? Sure. Well, we are in a sea of air. We're surrounded by air. So the air is pushing on us. So on us, there's something called P atmosphere. The air is pushing on us all the time. Right now. We're just used to it. We don't feel it. You know what that number is? 1.01 times 10 to the 5th. That's atmosphere pressure. Newton per meter squared, or 101,000. It's called P atmosphere. A lot of times when you're looking, so this is P at, atmosphere. Barometric pressure there, 1 bar is equivalent to 10 to the 5th, or 1 P atmosphere. Which is approximately 1 atmosphere pressure. So these are some of the scales that your atmosphere pressure, you hear that a lot there. Let's look at my hand. There we go. Let's take an example with pressure on my hand. Here's my hand. My fingers. Here's my hand. When you look at your hand, now we know what the pressure on it right now. My hand's flat like this, so I have pressure pushing on it in all directions, by the way. That pressure surrounding us, pushing from the bottom, the top, the left, the right, all direction. The pressure is P atmosphere. Well, let me see how big my hand is. Pretend my hand is rectangular shape. The length of my hand is approximately, what, 18 centimeter? And the width of it is approximately 10 centimeters. Approximately. Notice here is not really 10. We'll go 9, 18 by 9. So I'm going to treat my hand as something with 18 centimeters long. And the width, I'm going to treat it as, what is it, 9 centimeters? So what is the force of the air pushing on my hand? What is that force equal to? Rho equals F over A. You can look at that, you can say F equals what? Rho times A. Just playing with the math. I'm looking for the force of pressure by the air on my hand. F, no, not F, I mean P. I said rho P, not rho P. Pressure, rho is mass time divided by volume. P, not rho. Pressure. P, not rho. F equals pressure times A. So what's the pressure? Isn't that atmosphere pressure? And what's the area? Isn't that length times width? .01 e to the fifth times 0.18 times 0.09. 1636 Newton. If I push all the right button. (1636 Newton). Well, how come you don't feel that? You know? Pushing on you. Why isn't your hand going down? If somebody's pushing on you with that pressure, because there's equal amount from the bottom pushing up on you. So you don't feel that. You actually want to feel it? Take an aluminum can, take a soda can, suck the air out of it. What will happen if you suck the air out of it? Collapses. Take a Ziploc bag when they freeze the steak, fish, or if you go fishing, you see in these commercials, you want your food to stay fresh, use this machine that sucks the air out. What it does when you suck the air out, the outside pressure just locks everything in it because it pushes down, there's no air left there. You took all the pressure on the inside. When the can is open, the pressure from the inside equals the pressure from the outside. It's the same pressure. That's why it stays like in shape there. But once you suck the air out, that outside pressure is going to push on it, is going to crinkle everything. If you fly in an aircraft, they say please keep your seatbelt on all the time. Not just for turbulence. Because every once in a while, it's not often, we have an incident where we lose pressure. Or Air Hawaii, whatever that Hawaiian airline, a piece of fuselage went flying there. They lost a section of the plane, and 4 or 5 people, once that section blew up, it got sucked out because the pressure on the outside versus the inside difference. It sucked them out, and they were dead. They never found them. 5 people, I think. Here's the good news is, you're flying so high, the minute you're out there, you pass out immediately. There's no oxygen, pressure, you don't even know. So when you hit the ground, you're not even aware of it. There's the good side of it. You know, unless you're flying low, 12,000 feet, 13,000 feet, and there's pressure, there's oxygen, you're screaming all the way down. You know. You can text message while you're on the way down. You know. Now, if you decide to put air in your tires, you go today, you know, my tires, let me put some air on it. That's a pressure gauge. We use the gauge for that. And what that measures is actually the difference between the pressure and the air pressure, the atmosphere pressure. That's the gauge pressure. By the way, you can convert P atmosphere, which is 1.01 times 10. I don't have my chart with me, but I'll show you in this book here. You can convert from P atmosphere, P atmosphere, to pounds per square inch. That's approximately 14.7 pounds per square inch. You might have one in our book here, how you convert from, where's my book here? From any pressure to atmosphere to, where is it? Not this book. If I have the full-blown book, which is I don't have it with me, let me just take a look and see if this might have it. How to convert from atmosphere pressure to, we can Google that. We'll see that number is roughly 14.7. I thought this have it. The handout I gave you actually on the website, I put a handout. Let me look and see. I'm sure I have it here because I took it from the book. And that has the conversion factor on it. Let's see what that number is. Not on this one, Physics 1, I think.
What are you looking for?
The conversion factor from atmosphere pressure to pounds per square inch. Look for pressure, Mike.
1 atmosphere is
14.7, yep, pounds per square inch, yeah. So that's the conversion factor. Yeah. Okay, so that's pressure versus we talked about not versus, but pressure and density. This topic is pressure, how we calculate pressure. Again, when you measure the pressure in your tires, it's called gauge pressure, which is the difference between the pressure of the tire and the atmosphere pressure, the difference between them. That's what you're getting. So if the gauge pressure, when you measure that, is, for example, let's assume the gauge pressure says what? What's a tire at? 32? When you put them? 32 pounds per inch squared. What is the pressure on the inside of the tire? Well, the pressure then that's equal to 32 equals the pressure on the inside minus the atmosphere pressure, which is 14.7. That's where you're measuring the difference. So the pressure has to be a little bit more than 14.7, which is 32 plus 14.7, which is 46.7. And if you want to convert that to how many Pascal PA here, you go 46.7 pounds per inches squared over 1. 1 PA atmosphere pressure equals 14.7. The pressure is roughly 3 times the atmosphere pressure. 3.18 P atmosphere, or 3.18 times 1.01 times 10 to the 5th, which is approximately 3.2 times 10 to the 5th. That's the pressure inside that. 3 times the atmosphere pressure. Now, this takes us into another topic, which is scuba diving. Anyone does scuba diving? I'm a certified scuba diver. I was certified in Cancun. I had to go in a pool for about 30 seconds, and I was certified as long as they got my money. Done. But the way scuba diving, when you go in the water, you feel the pressure of the water on you. And the deeper you go, the more pressure. If you go 100 feet deep, there's a lot of pressure on you. So when you come up, you better come up slowly, because if you come up too fast, you are in trouble. So we're going to talk about that pressure. Let me stop this video. I'll make a new video on that.